Welcome, future chemists and medical professionals, to the deep dive. Today, we're embarking on a crucial journey, one that really lays the very foundation for your success in competitive exams. You know the ones, the Joint Entrance Examination, JE Main and Advanced, and the National Eligibility Entrance Test, NEET, and of course your Class 11 and 12 board exams. Our mission today is to truly unpack organic chemistry, some basic principles and techniques. Joining me to navigate this fundamental unit is our expert guide.
Thank you. It's a pleasure to be here. Organic chemistry, you see, it's not just a subject. It's the very fabric of our world, from the DNA that defines us to the proteins building our bodies, the clothes we wear, fuels we burn, and the life-saving medicines we rely on. Organic compounds are simply everywhere.
It's incredible when you think about it.
Absolutely.
Yeah.
Historically, back in the late 18th century, chemists actually believed organic compounds could only arise from living organisms. This was the vital force theory, proposed by Berzelius.
Ah, yes, the vital force.
Exactly. It suggested some kind of mysterious life force was absolutely essential for their creation.
Seems strange now.
It does. But then a huge shift occurred in 1828. A German chemist, Friedrich Wöhler, he famously debunked this theory. He synthesized urea, a distinctly organic compound, directly from an inorganic salt, ammonium cyanate, right there in his lab.
Wow, that must have been revolutionary.
Completely. And the reaction was quite elegant, really simple. Ammonium cyanate, NH4CNO, just transformed into urea, and H2CONH2. This breakthrough was quickly followed by Kolbe's synthesis of acetic acid in 1845, and then Berthelot creating methane in 1856. All from non-living sources.
So that just blew the vital force theory away.
Pretty much. These pioneering achievements ushered in the modern era of organic chemistry, an era fundamentally rooted in our understanding of, the electronic theory of covalent bonding. This history, in its vital context, it shows the journey of discovery leading to the principles we study today.
That historical leap, from vital force to lab synthesis is really astounding. It sets the stage perfectly for our first big question. What actually makes carbon so uniquely special, so extraordinary that an entire vast branch of chemistry is dedicated just to its compounds? What's its secret?
That's an excellent question, and it gets right to the heart of organic chemistry. Carbon's unparalleled uniqueness, its secret, if you like, lies primarily in its extraordinary property called catenation.
Catenation, okay.
Yes, imagine carbon as the ultimate set of Lego bricks for building molecules. Catenation is carbon's exceptional ability to form strong, stable, covalent bonds, not just with other elements, but crucially with other carbon atoms themselves.
Linking to itself.
Precisely. This remarkable self-linking capability allows carbon to form incredibly diverse molecular architectures. We're talking long, stable chains, intricate branch networks, and even robust ring structures of various sizes.
So it's incredibly versatile.
Extremely. But carbon isn't just about self-linking. It also readily forms strong covalent bonds with a variety of other crucial elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and the halogens, fluorine, chlorine, bromine, and iodine.
Right.
The study of these vast carbon-containing compounds, their immense structural variety, their unique chemical properties, their reactions, that's precisely what constitutes organic chemistry. It's like carbon is the universal connector, allowing for a near-infinite combination of molecular designs, #.1.2 tetravalence of carbon and shapes of organic compounds.
So carbon's knack for self-assembly and bonding with diverse partners is foundational. Its tetravalency, the ability to form four bonds, seems central to this. But how does this property, combined with something called hybridization, actually dictate the three-dimensional shapes of organic molecules? And, for students preparing for GE or NEET, why is visualizing these shapes so incredibly crucial?
You've hit upon a truly critical point there. Understanding the three-dimensional shapes of organic molecules is absolutely paramount. Why? Because molecular geometry profoundly dictates a compound's physical properties, its chemical reactivity, and even its biological function.
So shape is everything, essentially.
In many ways, yes. Carbon's tetravalency and its tendency to form stable covalent bonds are best understood through the concept of hybridization. This involves the mixing of atomic s and p orbitals to form new equivalent hybrid orbitals. These new orbitals are specifically tailored for bond formation, and they dictate the molecule's spatial arrangement.
Okay, hybridization.
Let's break down the three most common hybridization states for carbon. These fundamentally determine the geometry around a carbon atom, something you absolutely need to know for your exams.
Right.
First, we have sp3 hybridization. This happens when one s orbital and all three p orbitals mix. It forms 4 identical sp3 hybrid orbitals. Now, to minimize electron repulsion, these 4 sp3 orbitals arrange themselves in a tetrahedral geometry around the central carbon.
Like a pyramid.
Exactly, like a tiny pyramid with a carbon at its center. A perfect example is methane, CH4. Each CH bond in methane is a sigma bond, formed by the overlap of an sp3 orbital from carbon and a 1s orbital from hydrogen. The bond angles are approximately 109.5 degrees. So when you see a carbon forming 4 single bonds, almost always, it's sp3 hybridized and tetrahedral.
Okay, sp3 is tetrahedral. Got it.
Second, consider sp2 hybridization. Here, 1s orbital mixes with 2 p orbitals. This results in 3 equivalent sp2 hybrid orbitals. These 3 sp2 orbitals arrange themselves in a trigonal planar geometry.
Trigonal planar, flat triangle.
Precisely. Imagine a flat triangle with the carbon at the center and its 3 bonded atoms lying in the same plane. The bond angles are roughly 120 degrees, and the remaining unhybridized p orbital, it lies perpendicular to this plane. A prime example is ethene, C2H4. Each carbon atom is sp2 hybridized, forming that carbon-carbon double bond. Remember, a double bond consists of 1 sigma bond and 1 pi bond.
Okay, sp2 trigonal planar, 120 degrees.
Good. Finally, we have sp hybridization. This involves mixing 1 sp orbital and just 1 p orbital, forming 2 equivalent sp hybrid orbitals. These 2 sp orbitals orient themselves 180 degrees apart. So what shape is that?
Linear.
Exactly, a linear molecular geometry. The 2 remaining unhybridized p orbitals are perpendicular to each other and to the sp orbitals. The most common example is ethene, C2H2, or acetylene. Each carbon in ethene is sp hybridized, forming a carbon triple bond that's 1 sigma bond and 2 pi bonds. So if you see carbon with a triple bond or even 2 double bonds, think sp hybridized and linear.
sp3 tetrahedral, sp2 trigonal planar, sp linear. Okay.
Now, it's crucial for your exams to understand how this hybridization impacts bond properties, especially the s character. And sp hybrid orbital is 50%, BZ sp2 is about 33.3%, sp3 is only 25%.
More 6 character in sp?
Right. And since orbitals are closer to the nucleus than p orbitals, higher character means the hybrid orbital is closer to the nucleus, greater electron density there. What does that mean for the bonds?
Yeah, stronger bonds, shorter bonds.
You got it. Bonds formed by orbitals with higher sig character are generally shorter and stronger. So sig bonds are shorter and more robust than sp2 bonds, which are shorter and stronger than sp3 bonds. This directly affects bond length and bond enthalpy, the bond strength.
Okay, so sp2, sp3 for strength and shortness.
Correct. And this character also influences the electronegativity of carbon. A carbon atom with an sp3 hybrid orbital is actually more electronegative than an sp2 hybridized carbon, which is more electronegative than an sp3 hybridized carbon.
Really? Why is that?
Because electrons in an orbital with more cis character are held more tightly, closer to the nucleus. This increases the carbon atom's effective pull on shared electrons. This subtle difference, dictated by hybridization, can significantly influence a molecule's physical properties, like acidity and its chemical reactivity.
Yeah.
It's like carbon has these different personalities depending on its bonding, and those dictate shape and interaction.
Fascinating. Hashtag tag 1.2.1, some characteristic features of pi bonds.
To deepen our understanding of multiple bonds, let's zoom in a bit on the unique characteristics of pi bonds. Now, unlike sigma bonds, which are formed by head-on overlap, a pi bond forms when 2 p orbitals on adjacent atoms are oriented precisely parallel to each other. This allows for effective sideways overlap.
Sideways overlap. Okay.
Consider ethene again, H2CCH2. For that pi bond to form efficiently, all 6 atoms, the 2 carbons and 4 hydrogens, must lie perfectly in the same plane. The unhybridized p orbitals on each carbon are perpendicular to this molecular plane, ready for that side-by-side overlap.
So it's flat.
Exactly. Now, here's where it gets interesting. Try to imagine rotating one CH2 group relative to the other around that carbon-carbon double bond.
Uh-huh.
That rotational movement would severely disrupt the parallel overlap of those p orbitals. It would essentially break the pi bond. Therefore, rotation about a carbon-carbon double bond is highly restricted.
Ah, okay. So you can't just twist it freely like a single bond.
Precisely. And this restriction is incredibly important for a concept you'll learn later called geometrical isomerism, or cis-trans isomerism.
And right, cis-trans, I remember that.
Good. Another critical feature is the location of the pi bond's electron cloud. It's not strictly between the nuclei like a sigma bond. Instead, it's dispersed above and below the plane of the bonding atoms.
So it's more exposed.
Exactly. This makes the pi electrons more exposed and, crucially, more accessible to attacking reagents. Consequently, in molecules with multiple bonds, like alkenes or alkenes, the pi bonds generally represent the most reactive centers. They are the primary sites for many organic reactions, especially addition reactions. Knowing this helps you predict where a reaction is most likely to start.
That's a very clear explanation of why pi bonds are so reactive. Now, for success in exams like JG and NEET, it's absolutely vital to be able to, identify sigma and pi bonds and correctly determine the hybridization of carbon atoms. Can you maybe guide us through a common problem type?
Absolutely. Let's take this step by step, as visualizing bonds is key. Let's tackle problem 8.1a from the source material. How many sigma pi bonds are present in the molecule HCCH-CH3?
Okay.
To solve this, it's always best to mentally draw out all the bonds, including the implicit hydrogens. So HCCH, CHH, CH3. Let's label the carbons 1 to 5 from left to right.
Right.
Now let's count systematically. Remember the rules. A triple bond, always 1 sigma and 2 pi bonds between C1 and C2 here. A double bonds, pi bonds, always 1 sigma, 1 pi bond between C3 and C4 here. Single bonds, CC and CH. Always 1 sigma bond. Let's count sigma bonds first. CH bonds. There's 1 on C1, 1 on C3, 1 on C4, and 3 on C5. That's 1 plus 1 plus 1 plus 3 is 6 sigma CH bonds.
6 each sigmas.
Okay, now CSC bonds. C1 and C2 triple bond has 1 sigma part. Then there's the C2, C3 single bond. That's 1 sigma. The C3, C4 double bond has 1 sigma part. And finally, the C4, C5 single bond is 1 sigma. So that's 1 plus 1 plus 1 plus 1 plus 1 with 4 sigma CC bonds.
4 CC sigmas.
Total sigma bonds equals 6CH plus 4CC.
Yeah.
That's in sigma bonds. Now for the pi bonds. The C1 to C2 triple bond has 2 pi bonds. The C3-CC4 double bond has 1 pi bond. Total pi bonds 2 plus 1 equals 3 pi bonds. So HCCH3 has 10 sigma and 3 pi bonds.
10 sigma, 3 pi. Got it.
Now as practice for you, the listener, try applying the same detailed approach to problem 8.1b, which is CH2, CCH3. Take your time, count carefully. You should find it as 9 sigma and 2 pi bonds. Working through it yourself really helps solidify it.
Good advice.
Next, let's identify hybridization states, another frequent exam question. Let's look at problem 8.2b. What is the type of hybridization of each carbon in CH3-2CO? That's propanone or acetone.
Okay, acetone, right.
Again, visualize the structure. You have a central carbon double bonded to an oxygen and single bonded to 2 methyl groups,
Yeah.
CH3. The carbons in the methyl CH3 groups, each of these carbons is bonded to 3 hydrogens and 1 carbon, all by single bonds. That's 4 sigma bonds. So what hybridization?
4 sigma bonds. That's FP3.
Exactly.
Yeah.
sp3 hybridized. The central carbon, see cool, this carbon is double bonded to oxygen, 1 sigma, 1 pi, and single bonded to 2 methyl groups, 2 sigmas. So it forms a total of 3 sigma bonds and 1 pi bond. With 3 sigma bonds and no lone pairs, this central carbon
3 sigma, SP2.
correct, sp2 hybridized.
Okay.
For more practice, you should definitely apply this logic to the other parts of problem 8.2, like CH3Cl, CH3Cn, HTOM, H2, and CH3CH, Knowing how to systematically determine hybridization for each carbon is a must.
Absolutely.
And finally, let's briefly look at problem 8.3a. State of hybridization in shape for H2CO formaldehyde. The carbon atom is double bonded to oxygen, 1 sigma, 1 pi, and single bonded to 2 hydrogens, 2 sigmas. Total 3 sigma bonds, 1 pi bond. So the carbon is sp2 hybridized, and the shape around an sp2 hybridized carbon is
Trigonal planar.
perfect. Trigonal planar
Right.
with bond angles roughly 120 degrees. Imagine the O and 2 H's spread out flat around the carbon.
Makes sense.
Do practice the other parts, B, CH3F, and CHCN, to ensure you can confidently link hybridization to molecular shape. It's fundamental.
Knowing the 3D shapes is fascinating, but practically speaking, how do we effectively communicate these complex structures on, 2D paper or a screen? What are the different ways we represent organic compounds, moving from maybe very detailed to more abstract? And why do we even need these varied forms?
That's a great question, because representing structures really is the common language of chemistry. We've definitely evolved from extremely detailed drawings to highly efficient simplified notations. The most foundational way is the Lewis structure, or dot structure, showing all valence electrons. This often simplifies to the dash structure, where each 2-electron covalent bond is shown as a dash. Single dash, double dash, triple dash, easy enough.
Right, the basic lines for bonds.
Exactly. Sometimes lone pairs on heteroatoms like oxygen or nitrogen are shown. Sometimes they're omitted for simplicity. If you draw ethane, C2H6, ethene, C2H4, ethane, C2H2, or methanol, CH3OH, showing every single bond, that's your complete structural formula. Very explicit.
But probably time-consuming.
It can be. So moving towards more abstraction, we use the condensed structural formula. Here we omit some or all dashes and group identical atoms or groups together using subscripts. For instance, ethane, H3CCH3, just becomes CH3CH3. Ethene is H2CCH2, ethane is H3HCH, methanol is CH3OH. Even long chains, like an 8-carbon alkane, can be written as CH3, CH2, 6CH3. Saves space, shows repetitive units clearly.
More compact. Okay.
But for competitive exams, quick sketching, and just general communication in organic chemistry, the most common and abstract way is the bond line structural representation. This is where we use only lines to depict carbon bonds. And here's the crucial part. Carbon and hydrogen atoms are generally not explicitly shown. You have to infer them based on convention.
Ah, the skeletal structures.
Precisely. Here are the key conventions you must know. 1. Zigzag lines represent carbon chains. The zigzag implies the natural tetrahedral angles of sp3 carbons. 2. The terminals, the ends of the lines, represent methyl CH3 groups, unless something else is written there. 3. Junctions where lines meet or change direction represent carbon atoms. The number of hydrogens attached is implicit. You deduce it by remembering carbon forms 4 bonds. So a carbon at a junction with 2 lines coming off it must have 2 hydrogens attached, a CH2 group, to make 4 bonds total.
Okay, you just assume the hydrogens are there to make 4 bonds.
Exactly. 4 heteroatoms, anything other than C and H, like O and S, halogens are always explicitly written. Their attached hydrogens, if part of a functional group like AROH or NH2, are usually written too.
Got it.
Let's illustrate. Pentane, 5-carbon straight chain and bond line, is just a 5-point zigzag. Ends are CH3, internal points are CH2. Cyclohexane is just a hexagon. Chlorocyclohexane is a hexagon with Cl written attached to one corner. This graphical language might seem tricky initially, but it becomes incredibly efficient with practice, saves you precious time in exams.
Definitely seems faster once you get the hang of it. These different representations are vital for exams, where you often need to quickly interpret structures or convert between them. Let's maybe practice converting with a couple of problems.
Excellent idea. Let's work through problem 8.4a. Expand the condensed formula CH3CH2CO CH2CH3 into its complete structural formula.
Okay, 3-pentanone.
Right, how do we draw it completely? Start with the first CH3. C bonded to 3 H's. Bond that to a CH2. C bonded to 2 H's. Next is CO. That's a carbon double bonded to an oxygen CO. The C is also bonded to the previous CH2, then another CH2. C bonded to 2 H's connected to the carbonyl carbon. Finally, the last CH3. C bonded to 3 H's connected to the last CH2. So you've drawn out the full 5-carbon chain with the COs on the third carbon showing every single H.
Okay, that's clear.
Now, as practice, you should try converting CH3CH, problem 8.4b, into its complete structure. Pay attention to the double bond and those 3 repeating CH2 units.
Will do.
Let's go the other way now with problem 8.5.
Yeah.
For the compound HOCH2CH2CH2CH3CH3, write its condensed formula and its bond line formula.
Okay, that looks like a longer chain with branches.
It is. First, the condensed formula. You can group the repeating CH2 units. How many are there after the OH?
3 CH2s.
Right. Then you have a CH with a CH3 branch.
Yeah.
Followed by another CH with a CH3 branch and a CH3 at the end. So a good condensed form would be HOCH3, CH3, 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 CH3,
Okay, grouping the units.
Now, for the bond line formula, this takes a bit more thought. First, count the longest continuous carbon chain, starting from the HOCH2, 1, 2, 3, 4. Then the CH has a branch. Let's continue the main chain. 5, the next CH also has a branch. 6, and the final CH3 makes 7. So the parent chain has 7 carbons.
7 carbons in the main chain.
So draw a 7-point zigzag line. At the first carbon, one end of the zigzag, explicitly write HO. Remember, heteroatoms are shown. Now count along the zigzag from the HO end.
At carbon 5.
Draw a short line sticking off for the first CH3 branch. At carbon 6, draw another short line for the second CH3 branch. Remember, the ends and corners are implied carbons with enough hydrogens to make 4 bonds.
Okay, zigzag with OH at one end and 2 methyl branches near the other.
Exactly.
Yeah.
This conversion practice is crucial. Similarly, try problem 8.5b for HOCHCN2. And finally, make sure you practice problem 8.6. Expanding given bond line formulas back into complete structures showing all C and H atoms. It tests if you really understand the conventions. For each corner and end, place a C, count existing bonds, subtract from 4, add that many H's. It's systematic. Hashtag 2.2, 3-dimensional representation of organic molecules. Building on representing structures on paper, it's vital to remember that molecules exist in 3D. They're not flat. So to pick their 3D geometry on a 2D surface, we use specific conventions. The most common is the wedge and dash formula.
Ah, the ones with the solid and dashed triangles.
Exactly. We use 3 distinct line types to convey depth. 1, a solid wedge, like a filled-in triangle. This indicates a bond projecting out of the plane of the paper, coming towards you, the observer. 2. A dashed wedge, like a triangle made of dashes or lines. This depicts a bond projecting away from the plane of the paper, receding away from you, going behind the page. 3. A normal line, just a regular straight line. This represents a bond lying within the plane of the paper. Flat on things.
Oh, okay. Solid towards, dashed away, line in the plane.
Perfect. Take methane, CH4. To show its tetrahedral shape, you draw 2 CH bonds with normal lines in the plane. Then 1 CH bond as a solid wedge coming out, and the 4th CH bond as a dashed wedge going back. This visually conveys the 3D geometry.
I can picture that.
Beyond paper, chemists and students often use physical molecular models for a more tactile understanding. These come in various forms. First, the framework model. It just shows the bonds, like a skeleton, good for seeing the angles and connectivity. Second, the ball and stick model, probably the most familiar. Balls are atoms, different colors for different elements. Sticks are bonds. Sometimes springs are used for double, triple bonds, making it a ball and spring model.
Right, the classic chemistry models.
Then there's the space-filling model.
Yeah.
This emphasizes the relative size of each atom based on its van der Waals radius. It shows the volume the molecule occupies. Atoms are shown as overlapping spheres, giving a sense of the overall shape and how atoms pack together.
So different models emphasize different aspects.
Precisely. And of course, today, advanced computer graphics are heavily used for dynamic, interactive 3D visualizations. Mastering these 3D representation methods is crucial for interpreting complex structures in your studies.
Okay, so we have ways to draw molecules in 2D and 3D, but with millions of organic compounds known and new ones popping up all the time, how do we even begin to organize them? A clear classification system seems absolutely essential. How are they broadly categorized based on structure?
Indeed, classification is the backbone for understanding such a diverse field. We broadly categorize organic compounds based on their structural features into 2 main types. First, we have acyclic or open-chain compounds. You'll also hear them very commonly called aliphatic compounds. As the name suggests, these consist of carbon atoms linked in straight or branched chains, but without forming any rings. They are the foundational structures.
Like alkanes, mostly.
Yes, simple examples include ethane, CH3CH3, a straight-chain alkane, isobutane, which is branched, and also compounds with functional groups like acetaldehyde, CH3CHO, and acetic acid, CH3COH, as long as they don't form a ring structure. These are your typical linear or branched arrangements. Second, we distinguish cyclic or closed-chain or ring compounds. Now, within this broad category, we have further important distinctions. A. Alicyclic compounds. These are essentially aliphatic cyclic compounds. They contain carbon atoms joined in a ring, but their chemical properties are largely similar to open-chain aliphatic compounds. Think of them as cyclic versions of alkanes, alkenes, or alkanes.
Okay, so rings but behaving like chains.
Pretty much. Common examples: cyclopropane, a 3-carbon ring; cyclohexane, a 6-carbon saturated ring; cyclohexene, a 6-carbon ring with 1 double bond. These are often called homocyclic if the ring is only carbon atoms. But sometimes other atoms, heteroatoms like oxygen, nitrogen, or sulfur, can be part of the ring, like tetrahydrofuran, a 5-membered ring with 1 oxygen. Their behavior still largely resembles aliphatic compounds. B. Aromatic compounds. This is a special and incredibly significant class. We'll dive deep into them later. What sets them apart is their unique stability and reactivity, stemming from specific electron delocalization in their rings.
Like benzene.
Exactly. Aromatic compounds typically include benzene and related ring compounds, often called benzenoid, like aniline, benzene with NH2, or naphthalene, 2 fused benzene rings. There are also non-benzenoid aromatic compounds like tropone, which don't have a benzene ring but still show aromatic properties. And just like alicyclic rings, aromatic rings can also contain heteroatoms, forming heterocyclic aromatic compounds. Common examples are furan, 5-ring with O, thiophene, 5-ring with S, and pyridine, 6-ring with N.
Lots of categories there.
It helps organize the vastness. And beyond structure, we also group them by functional groups into homologous series. Hashtag tags Thive 3.2 functional groups in homologous series. Building on classification, let's define 2 absolutely fundamental concepts: the functional group and the homologous series. A functional group is a specific atom or a characteristic group of atoms attached to the carbon chain in a particular way. Think of it as the molecule's control center for chemical reactivity.
The reactive part.
Exactly. It's primarily responsible for determining the compound's characteristic chemical properties, largely independent of the carbon chain's length or complexity. For example, the hydroxyl group, Sure. It's found in all alcohols like methanol, CH3OH, ethanol, CH3CH2OH, even isopropanol, CH3,2CHOH. And because they all have that OH group, they all react similarly with sodium metal to liberate hydrogen gas.
So the group dictates the reaction.
Largely, yes. Other common functional groups you need to know are the aldehyde group, tells you CHO, the ketone group, CO, and the carboxylic acid group, COH. Each gives a distinct set of chemical properties. Now, a homologous series is a group or series of organic compounds that all share the same characteristic functional group. The individual members are called homologs.
Like a family of compounds.
That's a perfect way to think about it. They can all be represented by a general molecular formula, and a defining feature is that successive members simply differ by a CH2 chain. This means a mass difference of 14 atomic mass units between neighbors. Examples you know well: alkenes, 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 haloalkanes, alcohols, alkanols, aldehydes, alkanols, ketones, alkanones, carboxylic acids, alkanoic acids, amines. Each one is like a family where siblings get bigger by adding one CH2 block.
Okay, that makes sense.
And just a quick note, a single compound can sometimes have two or more functional groups, either identical or different. These are polyfunctional compounds, and their reactivity is an interesting mix of the properties from each group. #Strandtag 3.3 Nomenclature of Organic Compounds, IUPAC system.
Right. With potentially millions of these compounds out there, having a systematic way to name them seems absolutely critical. Especially for competitive exams, getting the name right or figuring out the structure from the name is a fundamental skill. Can you explain the IUPAC system and why it's just so important?
You've touched upon a non-negotiable skill for anyone serious about JEE or NEET, mastering nomenclature. The sheer number of compounds demands a universal, systematic naming method. That's precisely what the IUPAC system from the International Union of Pure and Applied Chemistry provides. Its main importance: it allows you to directly link a compound's name to its precise chemical structure and vice versa. No ambiguity, one name, one structure.
Crucial for avoiding confusion.
Absolutely. Before IUPAC became standard, compounds often had trivial or common names, usually based on their origin or some property, like citric acid from citrus fruits or formic acid from ants. Formica is Latin for ant.
I've heard some of those.
Yes, and some common names like toluene or aniline, even Buckminster fullerene, are still widely used and accepted by IUPAC. But they lack the systematic predictability of the full IUPAC name. The general principle of IUPAC naming involves 1. Identifying the parent hydrocarbon, usually the longest continuous carbon chain or main ring. 2. Identifying any functional groups present. 3. Modifying the parent name with appropriate prefixes for substituents and suffixes for the principal functional group to construct the full name.
Okay, parent chain, functional groups, prefixes, suffixes.
It's exactly. Just a quick clarification. Hydrocarbons contain only C and H. They're saturated if they have only CC single bonds. These are alkanes. Unsaturated ones have at least one CF double or CSE triple bond. #tag 3.1 IUPAC nomenclature of alkanes. Let's start with the foundation. Naming alkanes. For straight-chain hydrocarbons, the names end in -hane. The prefix indicates the carbon count: methane 1C, ethane 2C, propane 3C, butane 4C, then pentane 5C, hexane 6C, heptane 7C, octane 8C, nonane 9C, decane 10C, and so on, using Greek prefixes. You need to know these up to at least 10 carbons cold. These form the simplest homologous series.
Methane, ethane, propane. Yeah, got those.
Good. Now, for branched-chain hydrocarbons, we introduce alkyl groups. An alkyl group is formed by removing one hydrogen from an alkane. Methane, CH4, becomes a methyl group in UCH3. Ethane becomes ethyl, and CH2CH3. Propane becomes propyl. The rule is replace ane with allyl. We use abbreviations too. Me-methyl, ethyl, pure, propyl.
Methyl, ethyl, propyl. Okay.
Now, alkyl groups themselves can be branched. You must recognize common branched alkyl groups like isopropyl, sec-butyl, isobutyl, tert-butyl, and neopentyl. Know their structures instantly. They appear everywhere in exam questions. Okay, now for the crucial part. The rules for naming branched chain alkanes. Pay close attention. These are frequently tested, step by step. Rule 1. Identify the longest carbon chain, your absolute first step. Find the longest continuous chain of carbons. This is your parent or root name. It might zigzag. If you see an 8-carbon straight chain but can trace a 9-carbon path, the 9-carbon path is the parent.
Always the longest continuous path.
Always. Rule 2. Number the parent chain. Number the carbons in the parent chain, starting from the end, that gives the branch alkyl group's substituents the lowest possible numbers. You might need a number from both ends and compare the locant numbers. The set with the lowest number at the first point of difference wins. So 2, 3, 6 is lower than 2, 4, 5.
Lowest locant numbers. Okay.
Rule 3. Name and position the substituents. Name the alkyl groups, methyl, ethyl, etc., and indicate their positions using the numbers from Rule 2. If there are different alkyl groups, list them in alphabetical order. Use hyphens to separate numbers from names. Example, 6-ethyl-2-methylnonon. Ethyl comes alphabetically before methyl.
Alphabetical order for different groups.
Rule 4. Handle identical substituents. If you have two or more identical substituents, two methyl groups, use prefixes. D2, tri3, tetra, 4, etc. Indicate all their positions, separating the numbers with commas. Example, 2-4-dimethylpentane. Crucially, these prefixes, D, tri, tetra, are not considered when alphabetizing. Dimethyl is alphabetized under M for methyl, not D.
Okay, D, tri, tetra don't count for alphabetizing. Important point.
Very important. Rule 5. Deal with equivalent positions. If numbering from either end gives the same set of locant numbers, but for different substituents, assign the lower number to the substituent that comes first alphabetically. Example, if you could number to get 3-ethyl and 6-methyl, or R6-ethyl and 3-methyl, you choose 3-ethyl-6-methyloctane, because ethyl comes before methyl.
Alphabetical order breaks ties in numbering.
Exactly. Rule 6. Naming branched alkyl groups. If a substituent alkyl group is itself branched, like sec-butyl or isopropyl, name it systematically. Number away there. The carbons of the branched alkyl group starting from the carbon directly attached to the main parent chain is number 1, and close the entire name of this complex substituent in parentheses. For alphabetical order, remember, iso and neo prefixes are considered part of the name. Example, isopropyl starts with I. But sec and tert prefixes are not considered. AG sec-butyl is alphabetized under B for butyl.
That parenthesis rule and the prefix alphabetizing is tricky.
It is. Requires practice. Rule 7. Tiebreaker for equal chain size. Sometimes you might find two different chains of the exact same maximum length. If that happens, choose the chain that has a greater number of side chains or substituents.
More branches win if length is tied?
Correct. It simplifies the naming by breaking molecule down into more smaller pieces.
Wow, that's a lot of rules. But these seem logical. Applying them seems key. Can you briefly walk us through problem 8.7c again, just to nail down that longest chain rule, which seems easy to mess up?
Absolutely. Problem 8.7c contrasts the incorrect name 5,2-ethylbutyl 3-ethyl-3-dimethylcane with the correct name 5,2-etyl-2-dimethylpropylnonane. The absolute core error in the incorrect name is violating Rule 1. Find the longest continuous carbon chain. If you look at the structure implied by decane, carbons, and then carefully trace all possible continuous paths, including the substituent, you'll discover a path that's actually 9 carbons long.
Ah, so the decane was wrong from the start.
Exactly. You have to explore all paths. Once you correctly identify the 9-carbon non-end as the parent chain, you number it correctly. Then you look at the complex group attached to position 5. Naming that substituent systematically, remember Rule 6, number from the point of attachment, use parentheses, gives you 2-ethylcell-2-dimethylpropyl. This problem perfectly illustrates why Rule 1 is paramount. Get the parent chain wrong, and the whole name collapses. Practice tracing chains.
Great example.
Now, a quick word on cyclic compounds. For a simple saturated ring, just add the prefix cyclo to the alkane name. Cyclohexane for a 6-carbon ring. If there are substituents, use the same rules. Number the ring to give lowest locants. List substituents alphabetically. Example, 3-ethyl, 1-golo-1-dimethylcyclohexane. Numbering starts with the carbon with the 2 methyls to give a level 1, then goes toward the ethyl to give it position 3. Hashtag 3.3.2 IUPAC nomenclature of organic compounds having functional groups. We've got alkanes down. Now let's systematically name compounds with functional group. Remember, the functional group is the reactive site, so its naming and position are critical. The procedure involves 2 main steps. 1. Identify the principal functional group. This is crucial because it determines the suffix of the parent name. Your study material, Table 8.4, lists functional groups with their prefixes if they are substituents, and suffixes if they are the principal group. You absolutely must memorize the priority order in that table.
Memorize the priority order. Okay.
2. Number the longest carbon chain that contains the principal functional group. And this numbering must ensure the carbon atom bearing that principal functional group gets the lowest possible number. The functional group takes precedence over substituents when numbering.
Functional group gets the lowest number.
Right. Now, for polyfunctional compounds, those with more than one functional group, that priority system from Table 8.4 is non-negotiable. You must choose one group as the principal functional group based strictly on that priority order. The compound is named based on that group using its suffix. All other functional groups become subordinate and are named as substituents using their appropriate prefixes.
Okay, so one boss group, others are prefixes.
Exactly. You need to know this priority order cold. Carboxylic acid, COOH, is highest. Then sulfonic acid, NaCl3H ester, acid COO, acyl halide, COCO, amide, -CN, aldehyde, CHO, ketone, CO, alcohol, amine, NH2, then alkene and CC, and finally alkene, and CC. Groups like alkyl, phenol, halo, nitro, alkoxy are always prefixes.
Wow, that's a list to memorize.
It is, but it's fundamental. Let's take an example. HOCH2, CH2, 4COCH3. It has an alcohol, AOH, and a ketone, CO, which has higher priority.
Checking the list. Ketone is higher than alcohol.
Correct. So it's named as a ketone, suffix 1. The HOH group becomes a prefix, hydroxy. We number the chain, 7 carbons total, to give the ketone the lowest number, which is position 2. The hydroxyl group ends up at position 7, so the name is 7-hydroxyheptane 2,1.
Okay, that makes sense. Priority dictates the suffix in numbering.
Precisely. Another important rule, if you have multiple functional groups of the same type, e.g. 2 alcohols, use prefixes like D, tri, etc. before the suffix. And importantly, use the full name of the parent alkane. For example, HOCH2CH2OH is ethane 1,4,2-diol, not ethane 1,2-diol. You keep the E of ethane. Same for multiple double or triple bonds. CH2CH2 is Buddha 1,3-diene, not but 1,4,2-diene.
Keep the E for diols, dienes, etc. Good tip. This is definitely a high-yield area for competitive exams applying multiple rules. Let's practice with one specific example from the source, say problem 8.8, part 3.
Excellent choice. Let's walk through problem 8.83.
Okay.
The structure has both a ketone CO and a carboxylic acid, DECI-COH group. Step 1, principal functional group. Look at the priority list. Carboxylic acid, COH, is way higher than ketone CO.
Right, COH wins.
So the compound is named as a carboxylic acid, suffix oic acid. The ketone group becomes a prefix, which is oxo. Step 2, number the longest chain containing the principal group. The carbon of the COA group is always carbon number 1. Counting from there, the longest chain is 6 carbons long. So the parent is based on hexane.
6 carbons, starting from the acid carbon.
Step 3, locate and name the subordinate group.
Okay.
Counting from C1, the MECI-COH carbon, the ketone group, CO, is at position 5. So we add the prefix 5-oxo, putting it all together, 5-oxyhexanoic acid.
5-oxyhexanoic acid, clear.
For practice, you should definitely try the other parts of problem 8.8, deriving names for structures like 6-methyloctane-3-ol or hexo-1VN5-line. And equally important, practice problem 8.9, deriving structures from names like 2-chlorohexene or pent-4 and 2-ol or 6-hydroxyheptanol. This back and forth is key for exams. Hashtag 3.3, nomenclature of substituted benzene compounds. Moving on to aromatic systems. Let's discuss naming substituted benzene compounds. Hugely important, frequently tested. For monosubstituted benzenes, one group attached, the IUPAC name is usually substituent prefix plus benzene, simple enough. Like nitrobenzene, bromobenzene.
Straightforward.
However, many common names are still widely used and accepted by IUPAC. You must know these. Methylbenzene is toluene. Methoxybenzene is anisole. Aminobenzene is aniline. Hydroxybenzene is phenol. These common names often become the base name for more complex derivatives.
Toluene, anisole, aniline, phenol. Got it. Must know those.
Absolutely.
Yeah.
Now for dissubstituted benzene, 2 groups. We indicate positions by numbering the ring carbons 1 through 6. The goal: assign the lowest possible numbers to the substituents. For example, if you have 2 bromines at positions 1 and 3, it's 1/3 dibromobenzene, not 1/5.
Lowest numbers again.
Yes, but for dissubstituted benzenes only, we also use the common prefix system. Ortho-O for 1/2 positions, meta-M for 1/3 positions, para-P for 1/4 positions. So 1,3 dibromobenzene is also M-dibromobenzene. You need to be comfortable with both systems.
Ortho, meta, para for 1,4, 1,3, 1,4.
Okay, but be careful. For tri or higher substituted benzenes, you cannot use ortho, meta, para. You must use numbers following the lowest locant rule. Often, if one substituent gives the ring a common base name like the methyl and toluene, you assign that carbon position 1 and then number the ring to give the other substituents the lowest possible numbers. List substituents alphabetically. Examples: 1-chloro-2,4-digyphosphorodinitrobenzene or 2-chloro-1-methyl-4-nitrobenzene. Here, toluene is the base, methyl is C1.
Only numbers for 3 or more substituents.
Got it. Finally, know the phenol group. When the benzene ring itself is treated as a substituent, C6H5, attached to, say, an alkane chain with a functional group making the chain the parent, the benzene group is called phenol, often abbreviated PH, like 2-phenylpropan-1-ol.
Benzene as a substituent is phenol. Okay, that's a lot for benzene, but crucial. Let's try deriving a structure from a name to lock it in. How about problem 8.10D?
Good idea. Let's work through problem 8.10D. Write the structural formula for 4-ethyl-1-fluoro-2-nitrobenzene. How do we tackle this systematically? Step 1, Base compound. It ends in benzene. So draw a benzene ring, hexagon with alternating double bonds or a circle inside. Step 2. Substituents and positions we have. 1 fluoro, fluorine F at position 1, 2 nitro. Nitro group, it's NO2 at position 2, 4 ethyl. Ethyl group, dash CH2, CH3 at position 4.
Okay, F at 1, nitro at 2, ethyl at 4.
Step 3. Draw it. Draw the hexagon. Pick any carbon, call it position 1, attach the F there. Now count around the ring, clockwise or counterclockwise, doesn't matter here, to position 2. Attach the NO2 group. Continue around to position 4. Attach the ethyl group, dash CH2, CH3. Just double check the numbering ensures the lowest set of locants. 1, 2, 4 is the lowest possible combination here.
Looks right. Breaking it down makes it manageable.
Exactly. That systematic approach is key for exam success.
We've spent a lot of time on naming and representing molecules based on their unique structures. But here's a fascinating twist. What happens when compounds share the exact same molecular formula, same atom, same count, but then show distinctly different properties? This brings us to the really important concept of isomerism, right?
Precisely. Isomerism is where organic chemistry gets particularly interesting and sometimes challenging. It's the phenomenon where 2 or more distinct compounds possess the identical molecular formula but exhibit different physical and chemical properties.
Same formula, different properties. Yep.
Exactly. These compounds are called isomers. The differences in their properties arise because their atoms are arranged or connected differently, either in their fundamental connectivity or just in their spatial orientation. It's like having the same set of Lego bricks but building entirely different structures.
Okay.
Isomerism is broadly classified into 2 main types. 1, structural isomerism. 2, stereoisomerism. Hashtag 4.2, structural isomerism. Let's first dive into structural isomerism. As the name suggests, structural isomers have the same molecular formula but differ fundamentally in their structures, specifically in how their atoms are linked together. Different connectivity patterns. We subdivide this further. First, chain isomerism, also called skeletal isomerism. This occurs when compounds have the same molecular formula but different carbon skeletons. The difference is straight chain versus branch chain. A classic example is C5H12. This formula represents 3 chain isomers. Pentane or N-pentane, straight 5-carbon chain. Isopentane, IUPAC, 2-methylbutane, 4-carbon chain with a methyl branch. Neopentane, IUPAC, 2-carry-2-dimethylpropane. 3-carbon chain with 2 methyl branches on the middle carbon.
All C5H12, but different shapes, different boiling points probably.
Exactly, different properties because the skeleton is different. Second, position isomerism. Here, the compounds have the same molecular formula and the same carbon skeleton, but they differ in the position of a substituent or a functional group on that skeleton. Consider C3H80. This can represent 2 position isomers, which are alcohols. Propan-1O, CH3CH2CH2OH. The H group is on the first carbon. Propan-2O, CH3CH3. The HH group is on the second carbon.
Same chain, just the iso-H moved.
Correct. Different position, different properties. Third, functional group isomerism. This happens when compounds have the same molecular formula but possess different functional groups. This leads to vastly different chemical properties because they belong to entirely different classes of compounds. Example, C3H6O. This formula can be propanol, CH3CH2CHO. An aldehyde, the HCHO group. Propanone, CH3COCH3. A ketone CHO group.
Same formula, but aldehyde versus ketone. Very different.
Very different indeed. Finally, metamerism. This specific type arises due to different alkyl chains on either side of a functional group, like an ether, O, secondary imine, and H or ketone. The functional group must be polyvalent, meaning it can mix 2 parts of the molecule. Example, C4H10O can represent 2 ethers that are metamers. Methoxypropane, CH3OCH2HCH3, methyl on one side of O, propyl on the other, ethoxyethane, CH3CH2OCHCHE3, ethyl on both sides of O.
Ah, so the distribution of carbons around the functional group changes.
Precisely. Same formula, same functional group class, ether, but different arrangement of alkyl groups around it. That's metamerism. Hashtag 4.3 stereoisomerism. So structural isomerism is about different connections. Stereoisomerism, on the other hand, is about differences in spatial arrangement. Stereoisomers have the exact same constitution, same formula, same sequence of bonds, but differ only in the relative positions of their atoms or groups in 3-dimensional space.
So connectivity is the same, but the 3D layout is different.
Exactly. This is often more subtle. These are isomers that can't be interconverted just by rotating around single bonds. Stereoisomerism includes important types like geometrical isomerism, cis-trans, often around double bonds due to restricted rotation, and optical isomerism, involving chirality, non-superimposable mirror images called enantiomers, crucial for drug action. We'll explore these fascinating types in detail later on. For now, Just know they exist and represent another layer of structural difference.
Okay, we've covered what molecules are, how they look, how we name them, even how they can have the same formula but be different. But the real excitement in chemistry happens when they change, when they react. It's like seeing a car, then its blueprint, but now we want to go under the hood and see how the engine actually works. That's where reaction mechanisms come in, isn't it? What are the basic components?
That's a perfect analogy. Structures tell us what, mechanisms tell us how. At its core, an organic reaction involves an organic molecule, which we usually call the substrate, interacting with an attacking reagent.
Substrate and reagent.
Yes. This interaction leads to breaking existing covalent bonds and forming new ones. This process might involve creating highly reactive, short-lived intermediates. And ultimately, it leads to the formation of products, often along with some byproducts.
Substrate plus reagent, maybe intermediates, then products.
Exactly.
Yeah.
So the general scheme is substrate plus attacking reagent, intermediate S, plus byproducts. The substrate is typically the molecule providing the carbon skeleton for the new bonds. The other reactant is the reagent. The essence is this dynamic process of bond breaking and bond making. A reaction mechanism is basically a detailed step-by-step description of this entire transformation. It tells you precisely about the electron movement, which electrons go where, the energetics involved, energy changes during bond breaking making, and the rates of transformation, how fast steps happen.
So it's the whole story of a reaction.
It is. And understanding it is profoundly important. It helps chemists understand why reactions happen, how to control them, get better yields, and critically, how to plan the synthesis of new complex molecules. In the next few sections, we'll unravel the fundamental principles governing how these transformations unfold. Hashtag 5.2 fission of a covalent bond. The first fundamental concept is how covalent bonds actually break. This is called fission. There are two main ways a bond can cleave. First, heterolytic cleavage. Think hetero meaning different. In this type, when the bond breaks, the shared pair of electrons, both of them, remains entirely with one of the two fragments.
Unequal breaking.
Exactly. The consequences are significant. One atom, usually the more electronegative one, takes both electrons. It gets a negative charge and usually a complete valence octet. The other atom loses the shared pair. It ends up electron deficient, often with only 6 valence electrons, and gets a positive charge. If this atom is carbon, we call it carbocation. Older term was carbonium ion.
Carbocation, positive charge on carbon.
Right. Example. Cleavage of bromomethane, CH3Br. Bromine is more electronegative. So heterolysis gives a methyl carbocation, CH3+, and a bromide anion, Br. The arrow showing electron movement starts at the bond and points to the Br. Now, carbocations are classified based on how many other carbons are attached to the positive carbon. Primary, 1 degrees, secondary, 2 degrees, or tertiary, 3 degrees. A C+ attached to one other C is primary, 2 others is secondary, 3 others is tertiary.
Primary, secondary, tertiary.
Politically, carbocations are highly unstable and very reactive because that positive carbon lacks a full octet. However, their stability increases significantly with substitution. Tertiary, 3 degrees, secondary, 2 degrees, primary, 1 degrees, methyl, CH3+. So CH3C+ is the most stable, simple one.
More substituted is more stable. Why is that?
Good question. It's due to electron donating effects like the inductive effect and, very importantly, hyperconjugation, which we'll discuss shortly. These effects help spread out or stabilize that positive charge.
Okay, we'll come back to hyperconjugation.
We will. Structurally, carbocations like CH3+ are trigonal planar. The positive carbon is Int2 hybridized with an empty p orbital perpendicular to the plane. That empty orbital is key to their reactivity. Heterolytic cleavage can also go the other way. If carbon is bonded to something less electronegative, like a metal, carbon might take the electron pair, gaining a negative charge. This forms a carbanion.
Carbanion, negative charge on carbon.
Correct. Carbanions are usually sp3 hybridized but have a distorted tetrahedral shape, like ammonia, due to the lone pair. They're also generally unstable and highly reactive. Reactions that proceed via heterolytic cleavage forming ions are called ionic, heteropolar, or polar reactions. Second type of fission, homolytic cleavage. Think homo meaning same. Here the bond breaks symmetrically. Each atom gets 1 electron from the shared pair. We show this using half-headed or fishhook curved arrows showing single electron movement.
1 electron goes to each atom.
Right. The result is the formation of neutral species, atoms or groups, that each have an unpaired electron. These are called free radicals. For example, homolysis of ethane's CC bond would give 2 methyl free radicals, CH3. Free radicals are also very reactive intermediates. Like carbocations, alkyl free radicals are classified as primary, secondary, or tertiary, and their stability follows the same trend, increasing with substitution. Tertiary, like CH3, 3Cr. Secondary primary methyl, CH3r. Reactions involving homolytic cleavage are called free radical homopolar or nonpolar reactions.
So two ways bonds break. Unequal, heterolytic, forming ions, and equal, homolytic, forming radicals. That's very clear. Can you show us another practical example of heterolytic cleavage using those curved arrows? Visualizing electron movement is so helpful.
Certainly. Let's work through problem 8.1 Hudgens C. Show the heterolytic cleavage of the bond in CH3Cr using curved arrow notation. Remember, a full curve arrow shows movement of an electron pair from electron source to destination.
Yeah.
In CH3 show, we have a bond between methyl, carbon, and copper metal.
Which is more electronegative. Carbon, definitely more than a metal like copper.
Right, so carbon will attract the bonding electrons more strongly. When the bond breaks heterolytically, the electron pair will go to the carbon. So the curved arrow starts from the middle of the CQ bond. The arrow points towards the carbon atom of the CH3 group. This indicates the electron pair shifts entirely onto carbon. The result: we form CH3, methyl carbanion, with a negative charge and lone pair on carbon, and Q plus copper ion.
Arrow from bond to carbon, forming carbanion and copper ion. Got it.
Exactly. This shows the formation of oppositely charged ions. You can apply the same logic to problem 8.11a, CH3, SCH3, sulfur is more electronegative than C, and B, CH3CN, nitrogen is more electronegative than the carbon it's bonded to, as practice. Now we know how bonds break. Let's look at the attacking reagents again. How do they interact with the substrate? Reagents are fundamentally classified based on their electron affinity. Nucleophiles and electrophiles. First, nucleophiles, often written as nucleid, showing a lone pair or negative charge. They are nucleus-seeking, meaning they are electron-rich species. They have an available electron pair they can donate to form a new bond.
Electron donors.
Exactly. So they attack electron-deficient centers, electrophilic centers, in the substrate, places with a partial or full positive charge. Examples include negatively charged ions with lone pairs, hydroxide, HO, cyanide, CN, alkoxides, RNH, carbanions, R3C, neutral molecules with lone pairs, water, H2O, alcohols, ROH, amines, RNH2, ethers, R.
Okay, lone pairs or negative charge makes them nucleophiles.
Generally, yes. Second, electrophiles, often written as E plus R. They are electron-seeking, meaning they are electron-deficient species. They want to accept an electron pair to form a new bond.
Electron acceptors.
Right. So they attack electron-rich centers, nucleophilic centers, in the substrate, places with high electron density like lone pairs or pi bonds. Examples include carbocations, like CH3+, which have a positive charge and incomplete octet. Neutral molecules with electron-deficient atoms, often due to polar bonds, like the carbon atom in a carbonyl group, C-, which is partially positive plus, or the carbon in an alkyl halide, R3CX, which is also eco plus there. Neutral molecules with incomplete octets, like boron trifluoride, BF3, or aluminum chloride, LCl3.
The positive charge or partial positive charge makes them electrophiles.
That's the general idea. In a polar reaction, the fundamental interaction is shown by a curved arrow starting from the electron-rich nucleophile and ending at the electron-deficient electrophile, electron pair movement.
Distinguishing between these two, nucleophiles and electrophiles, seems like a very common type of question for exams. Can you help us quickly categorize a few?
Absolutely. Let's look at problem 8.12a. Is HS a nucleophile or electrophile?
HS minus. It has a negative charge and lone pairs on sulfur. Sounds electron-rich.
Exactly. It can easily donate an electron pair, so it's a nucleophile. Now consider problem 8.12. Is BF3 a nucleophile or electrophile?
BF3. Boron only has 6 valence electrons there, right? Incomplete octet.
Perfect. It's electron deficient and readily accepts an electron pair. Therefore, it's an electrophile. You can apply this electron-rich, electron-deficient logic to categorize the others in problem 8.12, like C2H5O, CH33N, H2N, all nucleophiles, and C plus H3, CH3C plus AO, N plus O2, all electrophiles. Let's also identify an electrophilic center using problem 8.13a. Identify the electrophilic center in CH3CHO, acetaldehyde.
Okay, acetaldehyde, it has that C double bond O group.
Right, the carbonyl group. Oxygen is much more electronegative than carbon. So what does it do to the electrons in the CO bond?
Pulls them towards itself, leaving the carbon a bit positive.
Precisely. It creates a significant partial positive charge, now, plus, on the carbonyl carbon. This makes that carbonyl carbon the electron-deficient site, the electrophilic center, ready to be attacked by a nucleophile.
Makes sense. The carbon in the CO.
You should practice identifying the electrophilic centers in CH3CN. Think about the C triple bond and electronegativity, and CH3I. Think about the CI bond as well. Always look for atoms made electron deficient by bonding to more electronegative atoms. Hashtag 5.4, electron movement in organic reactions, refined. Just to refine our use of curved arrow notation, it's more than just drawing arrows, it's the language showing exactly how electrons redistribute and how bonding changes. Remember the key rule. A full curved arrow starts from where an electron pair is the source, a lone pair, a pi bond, even a sigma bond sometimes, and ends where that pair moves to the destination. An atom to form a lone pair, or a space between atoms to form a new bond.
Source to destination of the electron pair.
Exactly. And remember the distinction. Full-headed arrow. Movement of an electron pair, 2 electrons. Used in polar reactions. Heterolysis. Nucleophile attacking electrophile. Half-headed, or fishhook arrow. Movement of a single electron, 1 electron. Using radical reactions. Homolysis.
Okay, full arrow for pairs, fishhook for single electrons.
Crucial distinction. For example, showing the heterolytic dissociation of CH3Cl again. The full arrow starts in the CCl bond, the electron pair source, and points to the Cl atom, the destination where the pair ends up as a lone pair, forming CH3+ and CLA. This notation is fundamental for drawing and understanding any reaction mechanism. Hashtag 5.5 electron displacement effects in covalent bonds. Beyond bond breaking, the way electrons are distributed within a molecule, even in its stable state, profoundly influences its reactivity. These electron displacements can be permanent effects, always present due to the atoms or groups involved, or temporary effects, only occurring when an attacking region approaches.
Permanent versus temporary.
Right. The inductive effect and resonance effect are permanent. The electromeric effect is temporary. We also need to discuss hyperconjugation, another crucial permanent effect. Hashtag 5.5.1 inductive effect. The inductive effect is a permanent electron displacement that happens in sigma bonds. It arises simply due to a difference in electron negativity between 2 atoms forming a sigma bond. The electron density in the bond gets pulled towards the more electron-negative atom, making the bond polar. This polarity then influences adjacent sigma bonds, causing a sort of chain reaction of polarization.
Like a tug of war transmitted along the chain.
Good analogy. Take chloroethane, CH3, CH2Cl. Chlorine is much more electronegative than carbon, so the CCl bond is polarized. Electron density shifts towards Cl, making it away from the first carbon, C1, making it plus. This O plus on C1 then pulls a little electron density from the C2C1 sigma bond, making C2 slightly positive too.
So the effect gets passed along.
Yes, but it decreases rapidly with distance. It's usually considered negligible after about 3 sigma bonds.
Fades out quickly.
Exactly. Based on this, we classify substituents. Electron withdrawing groups, high effect, pull electron density away from the carbon chain via sigma bonds. Examples: halogens, FCl, Br, Si, nitro, NO2, cyano, Cn, carboxyl, COH, ester, COR, aryl oxides, or AP. Electron donating groups, plus I effect, push electron density into the carbon chain via sigma bonds. The most common examples are alkyl groups like methyl, CH3, ethyl, next CH2, CH3. They are weakly electron donating compared to hydrogen.
Minus I withdraws, plus I donates. Okay. This effect sounds fundamental for reactivity, changing electron density. Let's see how to apply it maybe to judge bond polarity.
Certainly. Applying it to predict bond polarity is common. Let's look at problem 8.14a, which bond is more polar, H3CH phases H3CBr.
Okay, CH versus CBr. Bromine is way more electronegative than hydrogen.
Right, so the electronegativity difference between C and Bro is much larger than between C and H. This means the electron density in the CBr bond is pulled much more strongly towards Br. Therefore, the CBr bond is significantly more polar than the CH bond. You can use the same reasoning for parts, B, H3C and H2 versus H3COH. O is more electronegative than N, and CH3CH3CH3CSH. O is more electronegative than S.
Makes sense. Bigger electronegativity difference, more polar bond.
Now, let's address problem 8.15, in which CC bond of CH3C2CDCC1Br, the inductive effect is expected to be the least.
Okay, CH3, CH2, Gs2Br. Let's call them C3C2C1Br. Bromine pulls electrons, B effect.
Right, so it pulls most strongly from C1, making the C1Dr bond polar. This makes C1 plus PR. C1 then pulls from C2, making C2D plus C2, then pulls weakly from C3, making C3T3. Where is the effect weakest?
Furthest away. So on the C2-C3 bond, or involving C3 anyway.
Yes, exactly. The inductive effect diminishes rapidly. It's strongest on C1, weaker on C2, and least felt on C3, and the C2-C3 bond. Hashtag 5.5.2 resonance structures. Beyond localized sigma bond effects, we have resonance structures. This is crucial for understanding molecules where electrons aren't neatly confined to single or double bonds, especially in conjugated systems. Often a single Lewis structure just fails to explain observed properties. The classic example is benzene, C6H6. If you draw it with alternating single and double bonds, Kekulé structures, you'd expect two different CC bond lengths. But experimentally, all 6 CC bonds in benzene are identical, 139 pm long, intermediate between typical single 154 pm and double 134 pm bonds. A single structure can't explain this uniformity.
Right, the classic benzene problem.
This is where resonance theory comes in. It says the actual structure isn't any single Lewis drawing. It's a resonance hybrid, a blend or average of two or more hypothetical structures called resonance structures, or canonical forms, contributing structures. These resonance structures are imaginary, only the hybrid is real. For benzene, the two Kekulé structures are resonance structures contributing equally to the real hybrid. We often draw it as a hexagon with a circle inside to represent this delocalization.
The hybrid is the reality. The structures are just ways to think about it.
Precisely. Another example, nitromethane, CH3NO2. You can draw Lewis structures with the NEO double bond to either oxygen. Experimentally, both NO bonds are identical in length. Again, the real structure is a resonance hybrid of the two forms. A key consequence is resonance stabilization energy. The actual hybrid structure is always lower in energy, more stable, than any single contributing resonance structure. This energy difference is the resonance stabilization energy. The more stable equivalent resonance structures you can draw, the greater the resonance energy and the more stable the molecule. Benzene is extremely stable due to resonance.
More resonance structures often means more stability.
Especially if they are low-energy equivalent structures. Now, rules for writing valid resonance structures. 1. Nuclei don't move. Only electrons, pi electrons, lone pairs, move between structures. Atoms stay in the same place. 2. Same number of unpaired electrons. Total electron spins must be conserved. You can't create or destroy unpaired electrons.
Okay, only electrons move, keep unpaired electrons the same.
And critically, how to judge the stability of resonance structures. Very important for exams. More covalent bond generally means more stable. Structures where all atoms except H have complete octets are highly favored. Minimize charge separation. Structures with fewer formal charges are better, if charges are necessary. Minimize charge separation. Structures with fewer formal charges are better, if charges are necessary. Put negative charge on the most electronegative atom, like O, N. Minimize charge separation. Structures with fewer formal charges are better, if charges are necessary. Put positive charge on the most electropositive atom, less electronegative, like C. Minimize charge separation. Structures with fewer formal charges are better, if charges are necessary. Structures with more dispersal of charge over multiple atoms are more stable than those where charge is localized.
Those stability rules seem key for deciding which structures contribute most. Drawing and evaluating these structures is a big topic for exams. Could you demonstrate with an example? Show the electron movement and judge stability.
Absolutely. Let's work through problem 8.17. Write resonance structures of CH2CHCHO, propionyl or acroline, and indicate relative stability. This molecule has a conjugated system. CAC double bond next to a CHO double bond. Electrons can delocalize.
Okay, conjugated system.
Let's start with the most obvious uncharged structure. Structure I, most stable. Structure I, most stable. CH2CHCHO. Structure I, most stable. Here, all atoms have octets, except H, no formal charges. This is usually the major contributor. Now, let's move pi electrons to get other structures. We can push the CC pi electrons towards the CHO group. Use a curved arrow starting from the CHU pi bond, pointed to the space between the central C and the CHO carbon to form a new CHE double bond there. But that would give the middle carbon 5 bonds. So, simultaneously, the Ca pi electrons must move on to the oxygen atom as a lone pair. Show this with another curved arrow starting from the CO bond and pointing to the O atom.
Okay, electrons flow towards the oxygen.
This gives us CH2, CH, CH error. Error in original thought process, redraw needed.
Correction. Let's push electrons from the CC towards the oxygen. Arrow from CC pi bond to the CC single bond. Arrow from C pi bond to the oxygen atom. Structure 2, corrected.
A positive charge develops on the first carbon, a double bond forms in the middle, and a negative charge with a lone pair forms on the oxygen.
Okay, positive on one end, negative on the oxygen.
Now, stability comparison. Structure I, no charges, is definitely the most stable. Structure 2 involves charge separation, which costs energy, making it less stable than I. However, it's still a significant contributor because the negative charge is on the highly electronegative oxygen and the positive charge is on carbon. All atoms, except the C+, still have octets. This charge distribution is relatively favorable.
So charge separation makes it less stable, but putting negative on O is good.
Exactly. You could imagine drawing another structure by pushing electrons the other way, putting negative charge on the first carbon and positive on oxygen. That would be structure 3. CH2 to CHCHO plus on day. This is very unstable and a minor contributor because oxygen is highly electronegative and doesn't want a positive charge, plus the first carbon lacks an octet. So the relative stability order is typically structure I, most stable, structure 2, less stable but significant, structure 3, very unstable, minor.
Okay, third. Yeah.
For practice, definitely try. Problem 8.16, resonance in the carboxylate ion CH3COO, and problem 8.18, explaining why certain structures for an ester are not major contributors. This helps internalize the rules. Hashtag 5.5.3 resonance effect, R or M effect. Building on resonance, let's define the resonance effect, also called the mesomeric effect, R or M effect. This is another permanent electron displacement. It's the polarity produced in a molecule by the interaction between a pi bond and a lone pair on an adjacent atom, or R between two pi bonds within a conjugated system. This effect is transmitted through the conjugated pi system.
So it's delocalization through pi bonds or lone pairs.
Exactly. There are two types. One, positive resonance effect plus R effect. Electron density is transferred away from an atom or group attached to the conjugated system, pushing electrons into the system. This increases electron density at certain positions, usually ortho and para in benzene rings.
Yeah.
Classic example, aniline, C6H5 and H2, the lone pair on nitrogen, NH2, delocalizes into the benzene ring. Groups that show plus R effect typically have a lone pair to donate, OH or NH2, NR2, halogens F-Cl, Br.
Plus R donates electrons into the pi system.
Correct. 2, negative resonance effect, Danchart effect. Electron density is transferred towards the atom or group attached to the conjugated system, pulling electrons out of the system. This decreases electron density at certain positions, again, often orthopara in benzene. Example, nitrobenzene, C6H5 and O2. The NO group strongly withdraws electron density from the ring. Groups showing NER effect usually have a multiple bond involving an electronegative atom that can accept electrons. NO2, DANG80CN, DANG80O3.
And your R withdraws electrons from the pi system.
Yes. Remember, this requires a conjugated system alternating single and double triple bonds for the effect to be transmitted. The resonance effect is a powerful, permanent influence on electron density, hugely impacting reactivity. Hashtag 5.5.4 electromeric effect, E effect. Now, in contrast to the permanent inductive and resonance effects, we have the electromeric effect, E effect. This is a temporary effect.
Temporary. Okay.
It's observed only in compounds with multiple bonds, CC, CO, CN, etc., and only in the presence of an attacking reagent. It involves the complete transfer of a shared pair of pi electrons to one of the atoms joined by the multiple bond. This happens on demand by the reagent. As soon as the reagent is removed, the effect vanishes.
So it only happens during the reaction itself.
Exactly. We show it with a curved arrow indicating the pi electron pair shifting. Two types. One, positive electromeric effect plus E effect. The pi electrons shift towards the atom to which the attacking reagent gets attached. Example, when H plus, an electrophile, attacks ethene, the pi electrons shift to one carbon, which then bonds to the H plus 2. Negative electromeric effect, B effect. The pi electrons shift towards the atom to which the attacking reagent does not get attached. Example, when CN, a nucleophile, attacks a carbonyl group, CO, the CO pi electrons shift onto the oxygen atom, making it O, leaving the carbon positive, C plus, for the CN to attack.
Okay, depends on where the reagent attacks relative to the electron shift.
Right. And if inductive and electromeric effects operate in opposite directions, the electromeric effect usually dominates because it's a complete electron shift, driving immediate reactivity. Hashtag 5.5.5 hyperconjugation. Finally, another crucial permanent effect, hyperconjugation. It's a stabilizing interaction involving the delocalization of sigma electrons from a CH bond of an alkyl group. But this alkyl group must be directly attached to an atom with an empty p orbital, like a carbocation, or to an unsaturated system like an alkene or benzene ring.
Delocalization of sigma electrons this time, not pi.
Exactly. Sigma electrons from an adjacent CH bond overlap with the neighboring pi system or empty p orbital. It's sometimes called no-bond resonance, although that term can be a bit misleading. Let's revisit the ethylcation, CH3C plus H2, to understand it. The C plus carbon is sp2 hybridized and has an empty p orbital sticking out. The adjacent methyl group, DAC-CH3, has CH sigma bonds. If one of these CH bonds aligns itself parallel to the empty p orbital, the electrons in that CH sigma bond can partially delocalize or spread out into the empty p orbital.
Sigma electrons overlapping with the empty p orbital.
Yes. Imagine the electrons in the CH bond sort of leaning over into the empty space next door. This overlap effectively disperses the positive charge from the C plus onto the adjacent atoms, the C and H of the methyl group. This delocalization, stabilizes the carbocation.
Spreading the charge makes it more stable.
Exactly. The more CH bonds are available on adjacent carbons, we call these alpha hydrogens. To do this, the more the charge can be dispersed and the more stable the carbocation. This perfectly explains the stability order we mentioned earlier. Tertiary, secondary, primary methyl. CH3Tc+ has 9 alpha hydrogens for hyperconjugation, CH3CH2+ has 3, and CH3+ has none.
So that's why more substituted carbocations are more stable. Hyperconjugation.
Precisely. Hyperconjugation also stabilizes alkenes, like propene, and alkylarenes, like toluene, through overlap of adjacent CH sigma bonds with the pi system.
Hyperconjugation is clearly critical for understanding stability, especially for carbocations, the favorite topic for JG and NEET. Can you just re-emphasize that stability order and why methyl is least stable based on this?
Certainly. Let's focus on problem 8.19 again, the stability order. CH3, 3C+, CH3, 2CH+, CH3, CH2+, C plus H3. It's all about the number of alpha hydrogens available for hyperconjugation. Alpha hydrogens are hydrogens on carbons directly attached to the C+, tert-butyl carbocation, CH3, 3C+, 3 methyl groups attached to C plus hen. Each CH3 has 3 alpha H's. Total equals 9 alpha hydrogens. Maximum hyperconjugation, maximum stability. Isopropyl carbocation, CH3, 2CH+, 2 methyl groups attached to C plot O. Total equals 6 alpha hydrogens, less stable than tertiary. Ethyl carbocation, CH3, CH2+, 1 methyl group attached to C plus O. Total equals 3 alpha hydrogens, even less stable. Methyl cation C plus H3, no alkyl groups attached to C plus no. Total equals 0 alpha hydrogens. No hyperconjugation is possible. Furthermore, the empty p orbital on C plus is perpendicular to the plane of the CA bonds, preventing effective overlap even if they are adjacent. This lack of hyperconjugative stabilization makes the methyl-cation the least stable, simple carbocation.
0 alpha hydrogens, no hyperconjugation, least stable. Got it. Hashtag 5.6. Types of organic reactions and mechanisms.
So having covered bond fission, reagents, and electron effects, we can briefly mention the main categories of organic reactions. Understanding the detailed mechanisms comes next in your studies, but knowing the types provides a framework. Broadly, we classify organic reactions into 4 main types. 1. Substitution reactions. One atom or group is replaced by another. 2. Addition reactions. Atoms or groups add across a multiple bond, CEC or CSCA. 3. Elimination reactions. Atoms or groups are removed, usually forming a multiple bond, often the reverse of addition. 4. Rearrangement reactions. Atoms within a molecule rearrange to form an isomer.
Substitution, addition, elimination, rearrangement. SAER.
Okay.
We'll explore the mechanisms for these in detail in later units.
Okay, so we know how molecules are structured, named, and how they react. But in the real world, after you synthesize something or extract it from nature, it's rarely pure, right? Purification seems like a really essential practical step. What principles do these methods rely on? You're absolutely right. Purification is an indispensable step in practical organic chemistry. Whether from synthesis or extraction, the desired compound is almost always mixed with impurities, unreacted starting materials, byproducts, solvents, other natural compounds. Isolating it in a pure form is critical for accurate characterization, analysis, and any further use.
Can't really study it if it's mixed with junk.
Exactly. The various purification methods all rely on exploiting differences in physical properties between the desired compound and its impurities. These differences could be in solubility, boiling point, melting point, volatility, like sublimation or steam distillation, adsorption characteristics for chromatography.
So you pick a method based on how the compound differs from its impurities.
Precisely. And how do we know when it is pure? The classic indicators are a sharp, constant melting point for solids and a sharp, constant boiling point for liquids. Pure compounds melt or boil over a very narrow temperature range. Impurities typically lower and broaden the melting range or raise the boiling point. Of course, modern techniques like chromatography and spectroscopy give us even more powerful ways to assess purity. Hashtag 6.2 common purification techniques. Let's go through the common purification techniques you'll encounter. Hashtag 6.2.1 sublimation. First, sublimation. You might remember this. Some solids turn directly into vapor when heated, skipping the liquid phase.
Solid to gas directly, like dry ice, sort of?
Yeah.
Or naphthalene balls?
Exactly like naphthalene, camphor, iodine, benzoic acid. This method is used to separate such sublimable compounds from non-sublimable impurities. You gently heat the impure solid. The pure compound vaporizes, moves to a cold surface like an inverted funnel cooled with wet cotton, and deposits there as pure solid crystals, leaving the non-sublimable gunk behind. Simple and effective for the right compounds. Hashtag 6.2.2 crystallization. Crystallization is probably the most common and powerful technique for purifying solid organic compounds. The principle relies on differences in solubility. You need to find a suitable solvent where your desired compound is, sparingly soluble at room temperature, appreciably soluble at higher temperatures, near the solvent's boiling point.
Poorly soluble cold, very soluble hot. That's the key.
That's the ideal scenario. The process generally goes like this. 1. Dissolve the impure solid in the minimum amount of hot solvent needed to get it all dissolved, making a near saturated solution. 2. If there are insoluble impurities, like dust, fill to the hot solution. 3. Allow the hot, clear solution to cool slowly. As it cools, the solubility of your desired compound drops sharply and it starts to crystallize out in pure form. 4. Why does this work? Because the impurities are usually present in much smaller amounts, and already they remain soluble even in the cold solvent. They stay behind in the solution, called the mother liquor.
So the pure stuff comes out as crystals, impurities stay dissolved?
Ideally, yes. Then you filter off the pure crystals, wash them with a tiny bit of cold solvent to rinse off mother liquor without redissolving the product, and dry them.
What if finding one perfect solvent is hard?
Good point. Sometimes you use a mixture of two miscible solvents. One where the compound is very soluble, one where it's barely soluble. You adjust the mixture to get that soluble hot, insoluble cold behavior. Also, if you have colored impurities, you can often remove them by adding a small amount of activated charcoal to the hot solution before filtering. The charcoal absorbs the color.
Activated charcoal for color.
Okay. And if the impurities have solubilities very similar to your compound, you might need to do repeated crystallizations, recrystallization, to get it really pure. Hashtag 6.2.3, distillation. Distillation is the go-to method for purifying liquids. It works based on differences in boiling points. Liquids vaporize at different temperatures. You heat the mixture, vaporize the component, then cool the vapor to condense it back to liquid, collecting it separately.
Boiling and condensing.
Right. Several types. 1. Simple distillation. Use it to separate. 1. Simple distillation. A volatile liquid from non-volatile impurities, like salt dissolved in water. 1. Simple distillation. 2 liquids with a big difference in boiling points, typically 25 Kelvin or degrees Celsius or more. Host speaker. Big boiling point difference. Expert speaker. Yes. Heat the mixture in a flask. The liquid with the lower boiling point boils first. The vapor goes into a condenser, cooled tube, turns back into liquid and drips into a collection flask. The higher boiling liquid stays behind. Example, separating chloroform, BP 61 degrees C, 334 K, from aniline, BP 184 degrees, 457 K. Easy separation. 2. Fractional distillation. Use this when the boiling points are close together, less than 25 K difference. Simple distillation won't work well here. Host speaker. Why not? Expert speaker. Because both liquids will vaporize significantly at similar temperatures. You need better separation. Fractional distillation uses a fractionating column placed between the flask and the condenser. This column is filled with packing material, like glass beads or rings, or has trays. Host speaker. The tall column with stuff inside. Expert speaker. Right. These provide a large surface area for repeated vaporization condensation cycles. As the mixed vapor rises, it cools slightly, condenses, then re-vaporizes. Each cycle enriches the vapor in the more volatile lower boiling point component. By the time the vapor reaches the top of the column, it's almost pure lower boiling component. It then condenses and is collected. Think of the column as having many theoretical plates, each performing a mini distillation. Host speaker. So it's like doing many simple distillations stacked up. Expert speaker. Exactly. Huge application. Refining crude oil in the petroleum industry into gasoline, kerosene, etc. 3. Distillation under reduced pressure, or vacuum distillation. Use this for liquids that have very high boiling points, or importantly, liquids that decompose if heated to their normal boiling point at atmospheric pressure. Host speaker. Liquids that break down when boiled normally. Expert speaker. Yes, the principle. A liquid boils when its vapor pressure equals the external pressure. If you reduce the external pressure using a vacuum pump, the liquid will boil at a much lower temperature. This allows you to distill heat-sensitive compounds without destroying them. Classic example, separating glycerol from spent lye in soap making. Glycerol boils at 290 degrees C normally and decomposes, but under vacuum, it distills nicely at 180 degrees C. 4. Steam distillation. This technique is specific for separating substances that are 4. Steam distillation. Steam volatile, vaporize readily with steam. 4. Steam distillation, immiscible with water. Host speaker. Doesn't mix with water, but carried by steam. Expert speaker. Correct. You pass steam from generator through the heated mixture containing your compound. The key principle, Dalton's law. The mixture boils when the sum of the vapor pressure of your compound, P1, and the vapor pressure of water, P2, equals the external atmospheric pressure. So P1 plus P2. Since P1 only needs to be part of the atmospheric pressure, the compound boils at a temperature lower than its normal boiling point, and also lower than water's boiling point. Host speaker. Boils cooler because water vapor helps push it out. Expert speaker. That's a good way to think of it. The mixture of steam and compound vapor condenses. Since they are miscible, they form separate layers in the collection flask and can be easily separated. Used for purifying things like aniline, essential oils, like eucalyptus oil, etc. Expert speaker. Hashtag tag 6.2.4 differential extraction. Next, differential extraction. This is mainly used to pull an organic compound out of an aqueous solution like water into an organic solvent where it's more soluble. The two solvents must be immiscible, don't mix like oil and water.
Using a solvent to pull the compound out of water.
Exactly. You take the aqueous solution containing your compound, add an immiscible organic solvent, like ether or dichloromethane, in which your compound dissolves better. Put it all in a separatory funnel, that pear-shaped funnel with a tap. Stopper it, shake well to mix the layers and allow the compound to transfer into the organic layer. Then let it stand. The layers will separate based on density.
The funnel with the stopcock at the bottom.
Right. You carefully open the stopcock and drain off the bottom layer, usually the denser aqueous layer. You're left with your compound dissolved in the organic solvent in the funnel. Repeat the extraction with fresh organic solvent, maybe once or twice, to get more product out. Then, you just evaporate the organic solvent, which is usually volatile, to get your pure compound back.
What if the compound isn't that much more soluble in the organic solvent?
Good question. If solubility is low, simple shaking extraction is inefficient. You'd use continuous extraction, where the organic solvent is continuously recycled, boiled, condensed, dripped back through the aqueous layer, to gradually extract the compound over time. Hashtag 6.2.5 chromatography. Finally, chromatography. This is an incredibly powerful and versatile set of techniques. The name comes from chroma, color, because it was first used to separate plant pigments. Now it's used for separating complex mixtures, purifying compounds, and testing purity.
The colored bands separating on paper or in a column?
That's the classic image. The basic principle involves distributing the components of a mixture between two phases. A stationary phase, fixed, doesn't move, can be solid, like silica gel, alumina, or a liquid coated on a solid. A mobile phase moves over the stationary phase. Can be a liquid solvent, a mixture of solvents, or a gas.
Stationary and mobile phases.
You apply the mixture to the stationary phase. Then the mobile phase flows over it. Components of the mixture travel with the mobile phase, but they interact differently with the stationary phase. Components that stick strongly to the stationary phase, strong adsorption or low solubility in mobile phase, move slowly. Components that stick weakly, weak adsorption or high solubility in a mobile phase, move quickly. This difference in movement causes separation.
Different speeds lead to separation.
Exactly. Two main types based on the principle. A. Adsorption chromatography. Separation based on differential adsorption onto a solid stationary phase, adsorbent. Column chromatography. You pack a glass tube column with the adsorbent, like silica or alumina, apply the mixture solution at the top, then you pass a solvent, the eluent, which is the mobile phase, down the column. Components separate into bands moving down at different rates. You collect the fractions, eluents coming out the bottom one by one. More strongly adsorbed, slower, comes out later. Thin layer chromatography, TLC. Much faster, used often for quick checks. You use a glass plate coated with a thin layer of adsorbent chromoplate. Spot the mixture near the bottom. Place the plate upright in a closed jar with a shallow layer of eluent. The solvent moves up the plate by capillary action, carrying the components with it and separating them.
Like paper chromatography, but on a coated plate.
Similar principle, yes. After the solvent front nears the top, you take the plate out and mark the solvent front. You can then calculate the RF value, retardation factor, for each separated spot. RF, distance spot traveled from baseline, distance solvent traveled from baseline. RF values help identify compounds under specific conditions.
How do you see the spots if they're colorless?
Good point. Several ways. Shine UV light on the plate. If compounds absorb UV or the plate has a fluorescent indicator. Place the plate in a jar with iodine crystals. Many organic compounds absorb iodine vapor and show up as brown spots. Spray the plate with a specific staining reagent, like 9-hydrin for amino acids, which gives purple spots. B. Partition chromatography. Separation based on differential partitioning, distribution based on solubility, between a liquid stationary phase and a liquid or gas mobile phase. Paper chromatography, a classic example, uses special chromatography paper. The water molecules trapped in the paper's cellulose fibers act as the stationary phase, liquid. The solvent moving up the paper is the mobile phase, liquid. Components partition between the stationary water and the moving solvent. More soluble in mobile phase, moves faster. The developed paper strip is the chromatogram. Detection is similar to TLC, color, UV, stains. Chromatography is incredibly powerful, especially for separating very similar compounds in complex mixtures.
Okay, so we've purified our compound. Now, how do we actually confirm what elements are in it? Let's start with the basics. How do we prove the presence of the two most fundamental elements in organic chemistry, carbon and hydrogen?
Right. To detect carbon and hydrogen, the standard lab method is a controlled combustion test. You heat a small amount of the purified organic compound strongly with copper, oxide, CuO. The CuO acts as an oxidizing agent.
Burning it with copper oxide.
Exactly. Here's what happens and how we test for the products. 1. Any carbon in the compound gets oxidized by CuO to carbon dioxide, CO2. The reaction is C plus 2CuO, 2Cu plus CO2. The reaction is 2. How do we detect CO2? We bubble the gas produced through lime water, a clear solution of calcium hydroxide, COH2. If CO2 is present, it reacts to form insoluble calcium carbonate, CaO3, making the lime water turn milky or turbid. That turbidity is the positive test for carbon, the reaction. CO2 plus KCO3 plus H2O.
Milky lime water means carbon.
Okay. 3. Simultaneously, any hydrogen in the compound gets oxidized by CuO to water, H2O, which comes off as steam initially. The reaction, 2H plus CuO ET plus H2O, the reaction. 4. How do we detect this water? We pass the gas over anhydrous copper 2 sulfate, CuSO4. Anhydrous QSO4 is a white powder. If water is present, it hydrates the QSO4 to form hydrated copper, sulfate, CuSO4.5H2O, which is distinctly blue. The reaction, 5H2O plus CuSO4 white USO4.5H2O.
White powder turning blue means hydrogen?
Correct. So if you observe both the lime water turning milky and the anhydrous copper sulfate turning blue, it's definitive proof that the original organic compound contained both carbon and hydrogen. Hashtag 7.2 detection of other elements. Leucine's test. While C and H are almost always there, organic compounds often contain other elements like nitrogen, sulfur, halogens, Cl, Bri, and sometimes phosphorus. Detecting these requires different tests, and the most common approach for NS and halogens is Leucine's test, also called the sodium fusion test.
Leucine's test. Sodium fusion. Sounds intense.
It involves heating with metallic sodium, so it needs care. The core principle is clever. These elements, NSX, are usually covalently bonded in the organic molecule. The test converts them into ionic forms by fusing the compound with highly reactive metallic sodium.
Covalent to ionic using sodium.
Exactly. During the fusion, if nitrogen is present, along with carbon, it forms sodium cyanide, NaCN. If nitrogen is present, along with carbon, it forms sodium cyanide, NaCN, Na plus C plus NaACN. If sulfur is present, it forms sodium sulfide, NaCN, Na plus C plus S, Na2S ionic. If a halogen X is present, it forms the sodium halide, NaX. If a halogen X is present, it forms the sodium halide, NaX. If a halogen X is present, it forms the sodium halide, NaX. Na plus X, NaX, where X equals ClBr or I, ionic.
Okay, so you get sodium, cyanide, sulfide, or halide.
After the fusion, heating a small piece of sodium with the compound in a tube until red hot, you carefully plunge the hot tube into distilled water and boil it. This dissolves these ionic sodium salts, creating the sodium fusion extract. We then use portions of this clear extract for specific tests. A. Tests for nitrogen. Take some extract, add iron, sulfate, FeSO4 solution, boil gently, cool, and then carefully add concentrated sulfuric acid down the side of the tube. If nitrogen was present, as NaCN, you'll see a characteristic Prussian blue color or precipitate.
Prussian blue means nitrogen.
Yes, the chemistry is a bit involved. Cyanide ions react with F2+ to form hexacyanidofurate-2, FeSCN64. Acidification and heating might oxidize some F2+ to F3+. Then F3+ reacts with FCN64 to form the complex iron thehexacyanidofurate-2, a Fe4 Fe63, which is Prussian blue. B. Tests for sulfur. Two common tests. A. Acidify some extract with acetic acid, not HCl or H2SO4. Then add lead acetate solution. A black precipitate of lead sulfide, PBS, means sulfur was present as Na2S. Two common tests. B. To another portion of extract, add a few drops of sodium nitroprusside solution. A beautiful violet color confirms sulfur.
Black precipitate with lead acetate, OR violet with nitroprusside means sulfur.
Right. Now, an important point. What if the original compound had both nitrogen and sulfur?
Oh, no. Do they interfere?
They can. During fusion, they might react together to form sodium thiocyanate, NaSCN, Na plus C plus N plus SS NaCN. If NaCN is formed, then when you do the nitrogen test, adding FeSO4H2SO4, which generates Fa3+, you won't get Prussian blue. Instead, you'll get a blood red color due to the formation of iron 3 thiocyanate complex. So a blood red color indicates both N and S were originally present. If you want to test for them individually in this case, you need to repeat the fusion using excess sodium, which helps break down the NaCN back into NaCN and Na2S.
Okay, blood red means N and S together. Need excess sodium to test separately.
C, test for halogens, C-BRI. Take some extract, acidify it with dilute nitric acid, HNO3. Crucially, boil the solution for a minute or two. Why? To destroy any NaCN or Na2S that might be present, as cyanide and sulfite ions would interfere with the test by also forming precipitates with silver ions. After boiling and cooling, add silver nitrate, AgNO3 solution.
Acidify with nitric acid, boil, then add silver nitrate.
Yes. Now observe the precipitate. White precipitate, soluble in ammonium hydroxide, NH4OH, confirms chlorine, AgCl. Pale yellow precipitate, sparingly soluble in NH4OH, confirms bromine, AgBr. Bright yellow precipitate, insoluble in NH4OH, confirms iodine, AgI.
White soluble Cl, pale yellow sparingly soluble Br, bright yellow insoluble I. Got it.
D, test for phosphorus. For phosphorus, you first need to oxidize it to phosphate. Heat the original compound strongly with an oxidizing agent like sodium peroxide, Na2O2. This converts P to phosphate, PO43. Extract the fused mass with water, boil with concentrated nitric acid, and then add ammonium molybdate solution.
Oxidize to phosphate, then add ammonium molybdate.
Right. A yellow coloration or a yellow precipitate, ammonium phosphomolybdate, NH4,3PO4.1 confirms the presence of phosphorus. These qualitative tests are essential for identifying the elements present, a key step before quantitative analysis.
Okay, qualitative tests. Tell us what's there. But for really nailing down the identity of a compound, especially getting its empirical and molecular formula, we need to know how much of each element is present. That's quantitative analysis, right? How do we do that?
Exactly. Moving from what to how much is the core of quantitative analysis. Determining the mass percentage of each element in a pure organic compound is absolutely fundamental. As you learned way back in stoichiometry and mole concept, this percentage composition is what allows us to calculate the empirical formula, the simplest whole number ratio of atoms, and then, if we know the molar mass, the molecular formula, the actual number of atoms. Without accurate quantitative data, we can't truly know the compound's identity. So we use precise analytical methods for this. Hashtag 8.2 carbon and hydrogen estimation. Happily, carbon and hydrogen can be estimated together in one experiment, the combustion method, often called Liebig's method. The principle is simple. Take a known mass of the pure organic compound, weigh it accurately. Then burn it completely in an excess of pure oxygen, usually passed over a heated copper oxide, CuO, to ensure complete oxidation.
Burn it completely again.
Yes, but this time we measure things carefully. All the carbon in the compound converts quantitatively to carbon dioxide, CO2. All the hydrogen converts quantitatively to water, H2O. The general reaction: CXHY plus O2 AXXCO2 plus Y, 2H2O, balanced with excess O2. The method involves passing the gaseous products, CO2 and H2O, through a series of pre-weighed absorption tubes. 1. First, the gases pass through a tube containing anhydrous calcium chloride, KCl2, or magnesium perchlorate. This absorbs only the water. You weigh the tube before and after. The increase in mass gives you the mass of H2O, let's call it M1, produced.
Anhydrous KCl2 absorbs water.
Next, the remaining gas, now just CO2 and excess O2, passes through a tube containing a concentrated solution of potassium hydroxide, KOH, or soda lime. This absorbs only the carbon dioxide. Again, weigh the tube before and after. The increase in mass gives you the mass of CO2, let's call it M2, produced.
KOH absorbs CO2.
Right, so if you started with M grams of organic compound and produced M1 grams of H2O and M2 grams of CO2, you can calculate the percentages. Percentage of carbon. Percentage of carbon. We know CO2, molar mass 44, contains carbon, atomic mass 12. Percentage of carbon. So the mass of carbon in mid 2 grams of CO2 is 1244, mid of 2, percentage of carbon. Percentage C, mid of C, that's a compound, 100, percentage of carbon. Percentage C equals 1244, M and 2 integers. Percentage of hydrogen. Percentage of hydrogen. We know H2O, molar mass 18, contains 2 hydrogens, total atomic mass 2. Percentage of hydrogen, so the mass of hydrogen, M1 graph H2O is 218, M1, percentage of hydrogen. Percentage H, mass of compound 100. Percentage of hydrogen, first H, 218, M1 meter, 100.
Okay, those formulas look straightforward. Based on the mass of CO2 and H2O collected, let's quickly apply this to a numerical problem, like the ones we get in board exams.
Excellent idea. Let's work through problem 8.2 there again, focusing on the calculation. On combustion, 0.246 grams of an organic compound gave 0.198 grams of CO2 and 0.1014 grams of H2O. Calculate per scene and per stage. First, percentage of carbon, For C, percentage 1244, mass CO2 mass compound.
M at least 0.246 streams. M no is yields 0.198 grams. Acidity 8% or 44. 0.198, 0.246. 100, a 0.2727. Mass H2O 100 euro.
Now, percentage of hydrogen, percent HIC equals 218, mass H2O, mass compound 100.
M equals 0.246 and mass H2O 100, whereas manage equals 218, 0.10111, 0.4122, 100 equals 218. So the compound contains about 21.95% carbon and 4.58% hydrogen. You must be comfortable with these calculations. Hashtag 8.3 nitrogen estimation. For estimating nitrogen, there are two main methods you need to know. The Dumas method and K-Geldas method. Hashtag Dumas method. The Dumas method is quite general and accurate because it directly measures nitrogen gas.
Heat a known mass of the nitrogen-containing compound with excess copper oxide, CuO, in an atmosphere of CO2. All the nitrogen in the compound is liberated as nitrogen gas, N2. Carbon becomes CO2. Hydrogen becomes H2O.
Convert all N to N2 gas.
Yes. Any nitrogen oxides, NO formed, are reduced back to N2 by passing the gases over heated copper gauze.
Sure.
The resulting gas mixture, N2, CO2, maybe excess O2, is collected over an aqueous KOH solution.
KOH again, to absorb the CO2. Exactly. KOH absorbs the acidic CO2, leaving only the N2 gas to be collected in a graduated tube called a nitrometer. You measure the volume of N2 collected, V1, the temperature, T1, and the pressure, P observed. Now for the calculation. You need to correct the pressure for aqueous tension, the vapor pressure of water at T1. Let's call it F. So the actual pressure of dry N2 gas is P1 observed, F. Then convert the volume V1 at P1 and T1 to the volume at standard temperature and pressure, STP 273 K, 760 millihg or 1 atm. Volume at STP, VSTP, P1 V1 273, 760 T1.
Combine gas law to get volume at STP.
Right. Then you use the fact that 2400 ml or 22.4 L of N2 at STP has a mass of 28 grams. Molar mass of N2. So mass of N corrects 2400 VSTP in ml. Finally, percentage of nitrogen, mass of N, mass of organic compound.
Okay, so measure N2 volume, correct for pressure and temperature, convert to mass, then find percentage. Let's quickly run the numbers for problem 8.21.
Okay, problem 8.21. We 0.3 gram compound gave 50 ml N2 at 300 K and 715 millimeter pressure. Aqueous tension at 300 K equals 15 millimeters. P1 pressure of dry 50 millimeters, 50 millimeter. T1 equals 300 K. VSTP equals 750, 273, 760, 300, 700.9 milliliter. Mass of N 28, 22 5 per 100, 41.9 N over 0.052375 grams. N equals 0.052375, 0.3, 100, 500 at 17.46%. K-Geldas method. The second method is K-Geldas method. It's often simpler experimentally for certain types of compounds, but has limitations.
Convert all nitrogen in a known mass of the compound into ammonium sulfate, NH4-2SO4. You do this by heating the compound with concentrated sulfuric acid, H2SO4, often with a catalyst like CuSO4, and potassium sulfate to raise the boiling point. This step is called digestion.
Digest with sulfuric acid to get ammonium sulfate.
Yes. Then take the resulting solution, which contains NH4-2SO4, and heat it with an excess of strong alkali, usually sodium hydroxide, Na12.
Right.
Add base to release ammonia gas. All right. This ammonia gas is then absorbed into a precisely known excess volume of standard acid, usually standard H2SO4, NH3 plus H2SO4, excess NH4-2SO4 plus H2SO4, unreacted. Finally, you determine how much acid was not used up by the ammonia. You do this by back-titrating the remaining acid with a standard alkali, like standard NOH.
Titrate the leftover acid.
Yes. By knowing the initial amount of standard acid and how much was left over from the back titration, you can calculate how much acid reacted with the ammonia. From that, you calculate the amount of ammonia and thus the amount of nitrogen. Let's look at the calculation for problem 8.22. 0.5 gram compound, ammonia evolved to neutralize 10 milliliters of 1mH2SO4. Find percent. The reaction is 2NH3 plus H2SO4, NH4-2SO4. So 1 mole H2SO4 reacts with 2 moles NH3. We use 10 milliliters of 1mH2SO4. Moles H2SO4, molarity volume, L. OQ1M 0.010, L equals 0.01 moles. This must have reacted with 2.01 and 0.02 moles of NH3. Since 1 mole NH3 contains 1 mole N14G, 0.02, and we're going 0.28 grams of nitrogen. Mass of compound equals 0.5 grams a cent. Mass of compound 100 mil per 0.5. 100 is equal to 56.0%. Crucial limitation. K-Geldas method does not work for compounds where nitrogen is in a nitro group, that is NO2, or an azo group made as an N, or where nitrogen is part of a heterocyclic ring like pyridine. In these cases, the nitrogen isn't converted to ammonium sulfate during digestion. You must use the Dumas method for these compound types.
Important limitation to remember for exams. Nitro, azo, ring N, use Dumas. Hashtag 8.4, halogens estimation, Carius method.
For estimating halogens, CLBRI, the standard method is the Carius method.
Convert the halogen in a known mass of the organic compound into its corresponding silver halide, AgX, which is insoluble and can be weighed.
Precipitated as silver halide.
Exactly. You heat a known mass of the compound with fuming nitric acid and silver nitrate, AgNO3, in a sealed, strong glass tube called a Carius tube. The fuming HNO3 oxidizes the compound, C to CO2, H to H2O, and converts the halogen X into halide ions. X. These halide ions immediately react with the Ag+ ions from AgNO3 to precipitate as AgX, AgCl, AgBr, or AgI.
Heat in a sealed tube with nitric acid and silver nitrate.
Yes. After cooling and carefully opening the tube, you filter the precipitated silver halide, wash it thoroughly, dry it, and weigh it accurately. Calculation. Let mass of compound Mg, mass of AgX formed equals M1G, mass of halogen in M1 gram of AgX, atomic mass of X, molar mass of AgX, M1, percentage of halogen X, atomic mass of X, molar mass of AgX, M1 and meter 100. You need to know the atomic masses. Cl35.5, Br80, I127, Ag108.
Okay, weigh the AgX precipitate and calculate back. Let's do a quick numerical for bromine from problem 8.23.
All right, problem 8.23. 0.15 gram compound gave 0.12 gram AgBr. Find per hour. Atomic mass Br equals 80. Molar mass AgBr in 0.12 gram AgBr equals 80, 188.12. Additive is 0.05106 grams. Mass of compound equals 0.15 grams. Percent R equals 0.05106, 0.15, 0.15, 134.04%. Hashtag tag 8.5 sulfur estimation. For sulfur, we use a similar Carius tube method.
Oxidize all the sulfur in a known mass of the compound to sulfuric acid, H2SO4, then precipitate it as barium sulfate.
Oxidize S to sulfate, precipitate as BaSO4.
Right. Heat a known mass of the compound in a Carius tube with an oxidizing agent, sodium peroxide or fuming nitric acid. Sulfur gets converted to H2SO4. Then acid compound Mg, mass of BaSO4 formed M1G, atomic mass S was 32. Molar mass, BaSO4 plus 416 plus 233. Mass of sulfur in M1 gram of BaSO4 equals 32 to 33. M11, percentage of sulfur at 32 to 33, M11 meet all 100.
Similar calculation. Let's run through problem 8.24 for sulfur.
Okay, problem 8.24. 0.157 grams compound gave 0.4813 grams BaSO4. Find percents. Mass of S in 0.4813 grams BaSO4 using 3223, 0.4813 is 0.061 grams. Mass of compound equals 0.157 grams. 0.157, the rest 0.1% at 42.1%. Hashtag tag 8.6 phosphorus estimation. For phosphorus, again, the first step is oxidation.
Oxidize all phosphorus in a known mass of the compound to phosphoric acid H3PO4. Heat the compound with fuming nitric acid.
Oxidize P to phosphoric acid.
Yes. Then you precipitate the phosphoric acid in one of two main ways. One, as ammonium phosphomolybdate in H4 3PO4.1 3 add ammonia and ammonium lybdate solution. A yellow precipitate forms. Weigh this precipitate. Molar mass in 1877 contains 1 T atom, atomic mass 31. 1, as ammonium phosphomolybdate, NH4 3PO4.12PO3, percent P H2S 31, 1977, minimum liter 100, where M1 is massive yellow PPT. 2, as magnesium pyrophosphate, Mg2P2O7, add magnesium mixture to precipitate Mg2PO7, molar mass He222 contains 2 T atoms, total mass 62. 2, as magnesium pyrophosphate, Mg2P2O7, pp equals 62, 222 million meter 100, where M1 is mass of Mg2P2O7.
2 ways to precipitate and weigh the phosphorus. Hashtag tag 8.7 oxygen estimation.
Finally, oxygen. How do we estimate oxygen? Usually it's done by difference.
By difference, how?
You estimate the percentages of all other elements present, C, H, N, S, halogens, P, etc., accurately. Then you subtract the sum of all those percentages from 100%. The remainder is assumed to be the percentage of oxygen. Percent oxygen equals 100%. Sum of percent of all other elements.
So it's usually not measured directly.
Not usually in basic analysis. There is a direct method, though it's more complex. Briefly. 1, decompose a known mass of the compound by heating it in a stream of nitrogen gas. 2, pass the products over red-hot coke, carbon. Any oxygen released forms carbon monoxide, CO. 3, pass the CO quantitatively through warm iodine pentoxide, I2O5. The CO gets oxidized to CO2, and iodine I2 is produced. I2O5 plus 5C of I2 plus 5CO2. 4, you measure the amount of CO2 produced, or iodine liberated, and relate it back to the amount of oxygen in the original sample. Every mole of O2, 32G, eventually yields 2 moles of CO, which then yields 2 moles of CO2, 244.88 James. Percent oxygen, 32.88 mass of CO2, mass of compound, 100.
Okay, direct method exists, but difference method is common.
Yes. And just to mention, modern labs often use automated CHN elemental analyzers. You put in a tiny sample, milligrams, and the machine gives you per C, per H, and percent very quickly and accurately. But understanding the classical methods and principles is still essential for your foundation. Hashtag outro. So we've really covered a huge amount of ground today in this deep dive. We looked at carbon's uniqueness, catenation, hybridization, sp3, sp2, sp, and how that dictates shape. We covered representing structures, complete, condensed, bond line, even 3D wedge dash. Then the systematic classification and, critically, the IUPAC nomenclature rules for alkanes, functional groups, and benzene derivatives. We touched upon isomerism, structural types like chain, position, functional, metamerism, and then dived into reaction fundamentals, bond fission, heterolytic, homolytic, reagents, nucleophiles, electrophiles, and the crucial electron displacement effects inductive, resonance, electromeric, and hyperconjugation. Finally, we wrapped up with essential purification techniques like crystallization, distillation, chromatography, and the methods for qualitative and quantitative elemental analysis. Quite a foundation.
That truly was comprehensive and incredibly valuable for everyone listening. For all of you aiming high in your Class 11, 12 boards, and especially JG and NEET, please remember, consistent revision and dedicated practice are absolutely key. Go over this material again before your exams. Seriously, practice those past year questions applying these principles and problem-solving steps. And please feel free, reach out if you still have doubts about this chapter. We're here to help you succeed.
And as we finish, here's something to think about. How do these fundamental principles, carbons bonding, electron shifts, the ways we analyze molecules, how do they form the absolute bedrock for understanding the incredible complexity and diversity we see in organic reactions all around us? From making life-saving drugs to the very chemical reactions happening inside you right now. Keep exploring, keep questioning, keep learning.